Good evening, everyone, and welcome to this opportunity to meet astronomer Scott Kardel of the Palomar Observatory. 80 years ago, another astronomer, George Ellery Hale, thought big. Not content with observing the heavens through a telescope with a 40-inch diameter reflecting mirror, he lobbied for telescopes with a 60-inch and then a 100-inch mirror. The 100-inch mirror was made by the French glass-making giant Saint-Gobain and installed at the Mount Wilson Observatory in 1917. Then in 1928, Hale began a campaign for an even bigger telescope. He wrote these words: "Starlight is falling on every square mile of the Earth's surface, and the best we can do at present is gather up and concentrate the rays that strike an area 100 inches in diameter." His dream was a mirror of twice that diameter. Hale commissioned General Electric to make a 200-inch blank. It didn't work. And so in 1929, Hale turned to Corning Glassworks, who assigned the project to Dr. George Macaulay. Macaulay's team experimented with progressively larger blanks until, in 1934, they poured a huge quantity of molten Pyrex into a specially constructed mold, 200 inches in diameter. The attempt failed. Pieces of the mold broke loose, and the blank was ruined. That colossal wreck, of course, is now the largest single exhibit in our museum. Later that year, Corning tried again and succeeded. Now, for many of us in this room, that is the end of the story of the 200-inch disc. In reality, it was just the beginning. We're particularly fortunate to have with us this evening Scott Kardel, the Public Affairs Coordinator at the Palomar Observatory, who knows very well how the story continues. Scott received his Bachelor of Science degree in physical science with secondary education, and his master's in astronomy. In 2003, he became the Palomar Observatory's first full-time staff member devoted to public outreach, with the purpose of telling a wide range of audiences about Palomar's achievements in the exploration of the universe. Part of this outreach, of course, is his blog, Palomar Skies. Our current exhibition in the Raycow Library, Mirror to Discovery, owes much to Scott's willingness to share his encyclopedic knowledge. Will you please join me in welcoming Scott Kardel?
Thank you. That was a very nice introduction. I appreciate that. So it's my pleasure to be with you here this evening to talk about a place that I know well. So here is the 200-inch Hale Telescope at Palomar. The lights are not usually on at night, just so that you know. This, just for the picture. But the telescope is in use each and every clear night of the year, except at Christmas when we're closed. We, of course, couldn't do what we do in the world of astronomy from Palomar without what happened here at Corning. Now, this is where most people from this community last saw the mirror, in its packing crate on the train, ready to head westward. Of course, before that, I just wanted to let you know it's still there. This is as I saw the mirror in November, when we had pulled the mirror from the telescope to wash it. This is actually before it got its washing in November. And I came in early so I could take pictures of myself with the glass. So, but it's still there and still in use. And of course, none of that would be possible without the hard work that people did here first, in a variety of ways, from building the mold to, ladle, to ladling the glass, to not once but twice. I can tell you that the second mirror was poured on my mom's 5th birthday. She wasn't there, she wasn't part of the experience, but it makes it easy for me to remember December 2nd, 1934. And the crew that not only built the mold and ladled the molten glass and did all the hard work, of course, saved that mirror from floodwaters. Not once, but twice. That's the mirror in its case right here. To me, that's a terrifying photo. George Ellery Hale would have been terrified to have seen that as well, I'm sure. And then, yet, the job done here was professionally done. This fellow will take that piece of glass anywhere you want it to go. Is that the most confident person you've ever seen? I've seen this picture I don't know how many times, and I like it a lot, but this guy will take any cargo you've got, anywhere you want, and he's not going to sweat one bit about it. But the mirrors here, they of course took it down to the rail yard, carefully put it in place with just a couple of people to watch, and then took it cross country on what was an epic trip. 16 days across the nation, thousands of people out to see it. The advertising nicely placed, not here yet, but as you saw earlier. And then it gets to California. And at California, it was actually greeted by a larger crowd than it looks like here. That's you'll see in a moment, trust me. That's Edwin Hubble, by the way. Edwin Hubble used to like to tell people they were building the telescope for him, which was only partly true. He had made some major discoveries, and there were, of course, many other people eager to use the telescope as well. Now, I've heard stories about what had happened to this in its trip across the country. One of the stories is that there was bullets fired at it. And of course, there's steel plating here to protect the glass. I haven't actually seen proof of that, but when I scanned this picture about a year ago, I did notice this when you look at it really closely. Someone put their initials right there. So at one of the stops across country, HH, whoever that is, it's not Edwin Hubble, but someone scratched their initials on the side of the packing crate. Might have been one of the security guards that guarded it every night, I don't know. Of course, once it was lifted off the train, okay, there were more than 4 people there to see that in California. To me, this is another one of those photos that I think just captures a moment that's pretty exciting. You got the guy here who looks like he could die. People up here, a big crowd, police officers. But everyone is riveted on what's going on there, as 20 tons of glass and some more tons of steel are lifted into place. And so this was sort of a big moment, and then, of course, the whole thing was going to disappear into the optical shop at Caltech. And it was there for 11 and a half years, as people took the big flat disk and ground and polished that with to get the proper curve in it so that it could focus and collect starlight, and then to get that finer and finer and finer so there wouldn't be imperfections. Now, that story was interrupted by World War II. That's part of the reason why it was there for so long. Okay, if you take out 4 or 5 years for the war, that's still a very long time to work on that piece of glass. Once they announced it finished, it was again carefully packed up and sent up the mountain to Palomar. 3 semi-trucks to get it there. Oops, I'm sorry. They carried their own fuel. Those 2 in the back, I seem to have problems, are pushing to get it up the mountain. There's a good view of it for that job. He's here to make sure that they shift gears together in the right way at the right time. This was really good until they started getting higher up and into the fog and the sleet and the things that were coming down that day. But once it got to Palomar, we had a little bit more work to do on it, including putting the coating of aluminum to make it nice and shiny, but we discovered another example of graffiti. I can tell you that the mirror that was born here in Corning, Marcus Brown, the chief optician at Caltech, signed his name on it. Marcus H. Brown, that's O for October 3rd, 1947 AD. I'm sorry. Anyway, so finish things up. It's time to do some astronomy, right? So here is a relatively modern picture of the dome with the moon over it. There's the telescope. That's not an actual person, but it gives you a sense of scale. The mirror sits right here. And the way this works is light from the sky comes in, reflects off the big piece of glass, and then comes to focus up there, where we take its picture. We can also bounce the light down to another place to take its picture down here. Now, it used to be when the telescope was brand new, the astronomer had to ride at the very top to take the pictures. And there's Edwin Hubble posing for Life magazine. You can see the mirror here. You can see him there. And he took the first photos through the telescope in January of 1949. So 1949, but it was 1934 when the mirror was actually first cast. It's a long trip of cooling and annealing the mirror, rescuing it from a flood, sending it across country, grinding and polishing the glass, getting it up to the telescope, fine-tuning the telescope, and then getting ready to actually do some astronomy. Now, Edwin Hubble in astronomy became famous for discovering that galaxies were separate from the Milky Way and discovering that the universe itself was expanding. And so some of the, well, first I got to show you this. So this is the first picture taken through the telescope. I got ahead of myself. By Edwin Hubble. When you're Edwin Hubble, you get to take pictures of things named for you. This is Hubble's variable nebula. Collier's magazine had paid exclusive rights for the first pictures from the 200-inch telescope. I'm sure that probably factored into the naming, taking pictures of things named for yourself. But his chief interest really at that time wasn't clouds of gas in our own galaxy, but galaxies separate from the Milky Way. And it was the early mission of the telescope to try to be able to use it extensively to figure out how far galaxies are, how fast the universe is expanding, what's going on, will it expand forever, will it stop, will it collapse and fall back on itself. Now, Hubble himself actually died relatively early in the career of the 200-inch telescope. And so he didn't get to spend an extensive amount of time on this. But one of his students, an astronomer named Alan Sandage, who passed away just last year, took up the mantle of Hubble's research and spent the bulk of his entire career in astronomy working on answering just those questions. How fast is the universe expanding? Will it expand forever? And we certainly know a lot more about the universe and the answer to those questions than we did back then. Along the way, there were two people that more than once realized that the universe was in fact twice as big as anybody had ever imagined. One of those was a competitor, astronomer Martin Schmidt. It's not bad if you're an astronomer and you get yourself on the cover of Time magazine. He did that for the discovery of things called quasars. Quasars first found by radio telescopes. The optical astronomers at Palomar had a big enough telescope that they could look at these things and try to figure out what they were. There's a key technique that astronomers use to try to tell how far away something is, and whenever you applied that technique, everything looked crazy and it didn't make any sense. And it was Martin Schmidt that realized the reason it didn't make any sense was because what was happening was so extreme, the pattern of what you should see wasn't where it was supposed to be, it was someplace else. Basically, it was so far away And as the universe itself expands, the light from these things gets pushed more and more to the red because of the way that works, that this was not a star in our own galaxy like it looked like, but something at the other end of the universe. And it was a moment when people realized, wow, space is not only really big, but it's really, 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 really big. Much bigger than anyone had even imagined. And so we call these things quasars. For the longest time, people had no idea what a quasar really was other than a bright thing at the other end of the universe. And now we know that quasars are basically baby galaxies that have something that's called a supermassive black hole deep in their middle. And you might think that, well, then shouldn't it be black there? Well, it's not black because it's sucking stuff up. And as it does, that stuff gets really, really, really hot. And that's what makes the quasar glow bright enough that you can see it from all the way from the other end of the universe. It turns out, if I go back a little bit, that we now know that most galaxies, including our own Milky Way, have big, huge, gigantic, supermassive black holes at their cores as well. And that something you kind of have to wrap your mind around a little bit is that as you look farther out into space, you look farther back in time. And so this beautiful spiral galaxy is a relatively nearby galaxy that's a couple of tens of millions of light years away. And the quasar is billions of light years away. So it's almost like looking at a person at different ages in their lifetime. That maybe the galaxy I showed you a moment ago, when it was very young, looked much like a quasar and acted much like a quasar. And over time, these things change, just like we do as we age. Well, other early research that was very important with the 200-inch telescope was to understand stars, star clusters, how those work, how do stars themselves change over time. There was a lot of work done in terms of the formation of stars. And I can tell you that pictures like this, when I was like this, were inspirational and cool. You look now and you see lots of great pictures if you go on the internet from Hubble Space Telescope. Well, this was the Hubble Space Telescope of then in terms of cranking out pictures of the universe that people had never seen before. The Lagoon Nebula here is a beautiful cloud of gas and dust. It's in the process of forming a star cluster. You can see some of that cluster here. But it also represents something that was very new to astronomy. I'm going to show you two more examples of that. This particular shot is something called the Ring Nebula. That star there is in the process of dying, and this is sort of a bubble of gas that's been given off in the process of dying. This is a galaxy. I showed you a galaxy before. This is the Andromeda Galaxy. And the reason I show you the Ring Nebula and the Andromeda Galaxy is those are two examples of the first ever color pictures of space. You kind of take that completely for granted now because you see those all the time. But Palomar was where they first started using color astrophotography. And those two pictures were, I think, considered so advanced that they made it all the way into the future. And so that's not Photoshop. If you watch the first season of Star Trek and you're geeky enough about it like I am, you'll go, hey, wait a minute. Yeah, those are Palomar pictures up on the bridge of the Starship Enterprise. But think back then to the 1960s when this was being made. Those were considered futuristic things. And it turns out now that an amateur with their own backyard telescope and the kinds of equipment that are available to amateur astronomers now can take pictures just like those, just like the 200-inch telescope did in the 1960s and 50s. So technology's evolving in some ways that are pretty impressive. Of course, we can do some things now that amateurs can't. But this is the guy that pioneered that. His name is William Miller. He was posing for Life magazine and showing how that worked when you'd ride in the telescopes. This is where we saw Edwin Hubble before, loading in the color film. And of course, you have to remember that on a cold winter night, the astronomer will be up there maybe all night. So I know it's Southern California. You think, well, how cold can it get? Well, it snowed on Palomar last night, just like it snowed here yesterday. And if you're going to be up there for 10 hours in the dark by yourself, in the cold, taking pictures, bundling up is a good thing. But times have changed. We do astronomy in a different way now. Now, we send somebody up in the daytime, it doesn't look daytime, it's the dome is closed, who gets the electronic camera ready, and the astronomer sits in front of their computer in a warm room, close to the coffee, the bathroom, snacks, things are good. Oops. So times have definitely changed. Does the view look different? Yeah, there's a couple more wires now. There's some fiber optic. I'm trying to remember where that was made. Oh yeah, you probably know. So that's from Corning. There's a lot of that there, most of the orange stuff. Here's what it looks like in time-lapse when we change cameras, because we have more than one. So we're going to take one out of prime focus. It's actually the one that you just saw there, coming down. People are working really fast here. They're taking up another camera there, and they're going to load that into prime focus. So we have different cameras that are used depending on what the astronomers request. They have different abilities. The one that just went up is a camera that doesn't see the kind of light that you and I see. It sees into the infrared. The one that came down was one that does see more like the kind of light that you and I can see. So I want to give you an example of the difference. So here's an old photo from when I was about this big of something called the Orion Nebula. It's taken with the 200-inch telescope at prime focus. It's a beautiful thing that you can see in the sky with your own eye, with binoculars, with any kind of telescope. It just gets better the better your telescope is, but you can see it. Here's coming up a view of the same thing taken with the 200-inch telescope, but a camera that sees into the infrared. Doesn't look too similar. One of the advantages to going with a different kind of light is that you can see into the cloud. You can see more detail that you would otherwise not be able to see. It isn't entirely obvious in this picture that you have a cloud of gas that's in the process of forming a cluster of stars. The cluster of stars is certainly much more obvious here. Now, we always talk about the mirror, but there's really a bunch. So here's a drawing. The 200-inch mirror is here. We have 3 mirrors stashed up there. Another one here, another one here, another one there. All of those made here. It's a nice drawing by a fellow named Russell Porter, 1936, just showing where all of that stuff is. But you may or may not know that there's another mirror we got for our 48-inch telescope, also from Corning. I won't go into the reasons why our 48-inch telescope has a 72-inch mirror, but it does. That's what it looked like when they uncrated it the day it came. That doesn't look so nice, does it? That's okay, because it's then up to the opticians to fashion that surface into a nice reflective surface to collect starlight. Maybe you'll see if they did an okay job. What do you think? Kind of a contrast. Yeah, so there's the mirror when we pulled it out to get it recoded the last time, just as it was about to go back into the telescope. And that 48-inch telescope has really been a workhorse. That's how it used to be operated. So it wasn't made to look through. It was only made to take pictures. The film was loaded inside, and then someone would look through a finder scope to make sure it was pointed in the right place, and it would track across the sky in the right way. Oops, sorry. When I gesture sometimes, I change the remote. And its first mission was to map the whole night sky. Basically be a finder telescope for the bigger telescope on the mountain and for observatories around the world. So they produced something called the Palomar Sky Survey. This particular picture shows another part of Orion. That and that are 2 of the 3 stars of Orion's belt. The third one's up here somewhere. You've maybe heard of the Horsehead Nebula right there. This is called the Flame Nebula. And I want to just jump back to the 200-inch and show you that same thing, the Flame Nebula, but in the infrared. So again, changing wavelengths, you can see some pretty cool differences. Of course, you can get a much closer view from the bigger scope than the wide-angle telescope. Another thing that has happened recently is we've taken that 48-inch telescope and we've automated it. So it's in use every night with nobody there. It's pretty cool. It's got a 96 megapixel camera in it, and it takes pictures every 90 seconds all night long. Earlier, its main mission in this automation was to hunt for asteroids. We found a couple. Can you see the one right there? The streak? That streak is an asteroid, so basically they took the telescope and they pointed it and tracked it on the stars, and during the time of the exposure, the asteroid moved. And over the years at Palomar, we found over 27,500 asteroids. There's none that you need to change your plans over. Okay, things are good. We don't know of any that are on a direct collision course for the Earth, which is nice. So another more recent thing that's been an active part of the mission of the 48-inch telescope at Palomar has been to hunt for worlds in the outer solar system. And we're the guys that got Pluto in trouble. Yeah, I see. I was told there's an exit here if I need to use it. So this is just artwork. Here's a section of the Earth for scale. There's Pluto. And all of these other things are worlds of the outer solar system. This one is the one that's thought to be a little bit bigger than Pluto, Eris. But this one, this one, this one, this one, this one, and that one, all discovered at Palomar with the 48-inch telescope. And what's really happened, what's important isn't, is Pluto a planet or not a planet? What's important is we've discovered a whole lot of cool stuff about the outer part of the solar system. That there are more worlds there and more variety to those worlds than anybody had ever dreamed of. Especially in the time when we thought Pluto was big and alone and the only thing there. So Pluto was found in 1930, and it wasn't until 1992, 62 years later, that people began to find some companions to Pluto in the outer solar system. And now we know there's a lot of them and a great diversity to the kinds of worlds that are out there. But many of them are similar to Pluto in many respects, and that has something to do with the decision as to whether to classify it a planet or not. I know there are strong feelings on that issue. We could talk about those later if you want. But I'll tell you now that the main mission of this 48-inch telescope is to hunt for things that explode in the night, supernovae. Now, I've got two old pictures here that show the exact same thing, but taken many years apart, 1959, 1972. And you see what's obviously different, I hope. Wow, that wasn't there in the first picture. They happened to take this picture when a star was exploding in that galaxy. So it's pretty far away, and yet it's just about as bright as everything there. Pretty amazing. Now, if you look often enough, you'll find some of these, but, oops. I would say the astronomer here probably got lucky. You took one picture, compared it to an old one, and went, hey, look, it's different, then figured out what it was. If you want to catch these things in the act, you need to do it in a more systematic way, and that's what we're doing now. So when we see them close to us, we can see they're pretty spectacular things. This one was observed, it's called the Crab Nebula. It was observed by the Chinese in the sky in the year 1054. At night, it was bright enough that it cast shadows. Today, 1,000 or so years later, through the 200-inch telescope, it's a pretty impressive, complex thing, and basically you're looking at the guts of a star that has exploded, and the core of it's right there, something we call a neutron star. And every once in a while, when these things explode, they kind of explode in a way that sends them in one direction, like a rocket might if there was a big push on one end and it shoots that neutron star another way. So that's what this is. The neutron star is right there. This is what we call the Guitar Nebula, for hopefully obvious reasons. But this is essentially the wake, the wake of that star that's shooting through space as it shoots through a thin cloud of gas from an explosion that was not symmetrical, one that gave it a sideways kick. Well, we can see them in our own galaxy in great detail, but they don't happen very often. There hasn't been one of these in our galaxy since the telescope was invented. So if you want to wait for a close supernova, your wait's going to be a long time. But if you start looking at lots of other galaxies, you're going to catch some. You won't see them in detail, but you're going to see them in the act. And if you want to understand what's happening there, that's the thing to do. So what we do is we take that 48-inch telescope, the project is called Palomar Transient Factory, and we have it take pictures every 90 seconds, all night long. Take that data, beam it away on a big microwave dish to a place with a whole bunch of computers. Now remember, the telescope's automated, the place for the computers is now pretty much automated, and it takes new pictures as they come in. Now remember this picture? What we're going to do is we're going to take old pictures and new pictures and subtract them from each other. In this case, the supernova was obvious. Suppose it wasn't obvious. Well, that's what you get when you do a subtraction. Is it really obvious now? I think it's more obvious than here, wouldn't you say? Now, if the supernova was not here but there, would you notice it in this picture? Maybe not. It'd be lost in the light of the other galaxy. But if you combine them like this and subtract them that way, boom, they really pop out. Now, some of these galaxies are really, really, really far away, and the supernovae are too. So we can still use this technique, and it works pretty well. I'm going to show you a picture that is like a bunch of dots. Dots are pretty exciting, right? In this case, what's black and white has been reversed, and this is an entire galaxy, as are these things. And so this picture and this picture, we're going to subtract them from each other, and look, there's something there. That's a supernova. And they caught it before it actually got brighter. So what happens is, this is the part that's exciting, and the part that makes the automation really work is sometimes these things do their really most interesting stuff in a very short window of time, and if you miss it, you miss it. So by having the automated telescope and the automated system to look for this, you can then get the word out right away and get other telescopes on the track too. If you look at this nice picture of a galaxy, that's what they caught out of it. So if you were looking at two pictures like this, taken at different times and trying to compare everything in there, that's not an easy thing to do. It's a lot easier for the computer to be able to pop that out. So for galaxies that are somewhat close, we can find them, but for galaxies that are far away, we can do that too. Once they think they've got it, they beam it back to Palomar, and we confirm whether that's a real thing or not. Do follow-up observations with a second telescope, Corning didn't make that mirror, so I won't talk about that one, and then at the 200-inch as well. Basically, that telescope and telescopes in Hawaii and Arizona and other places are used to figure out what kind of a thing that is and what's going on with that. That's the count I checked earlier this afternoon. So far, they started the program almost 2 years ago, and they found over 1,000 supernovae. Using the old technique that I showed you, where you have the one picture and the other picture, and you just sort of hope and you look. The best guy ever at that found 120 in his life. We found over 1,000 in about 2 years. Not bad. So, other things. We go back to the 200-inch here. Have you been out at night and seen the stars twinkle sometime? Is that a good thing? Well, being out at night and seeing the stars, that's a good thing. The twinkling of the stars, is that a good thing? Actually, for astronomers, it's not. It's a bad thing. If you look at stars when they twinkle through a high-powered telescope, they might look something like this. They're supposed to be like little round dots. And so the image shakes and it wiggles and it wobbles and if you take a single picture over that time, what you're going to get is some blurriness. And we try to put telescopes in places where there's not a lot of that, but there's always some. And so there's a technique that's used now to be able to clean that up. We call it adaptive optics. This is before and that's after. This blur is in fact two stars, but you can't tell that until you use this technique. And so we do this with the 200-inch telescope. Remember, the mirror's here, and we can take starlight and bounce it off that up to here, where we can take its picture or put a second mirror that sends it down to there. And down there, we have an instrument that inside that is a sensor that tells how this stuff is messed up, and another mirror that bends. This mirror bends in 241 places, up to 2,000 times a second, to correct for what the air is doing to give us that sharp picture. just a little 6-inch mirror. And so with that, we can do things like take this picture and turn it into that, which isn't too bad. Or this is, if anyone ever goes to the website Astronomy Picture of the Day, earlier this week, this picture was featured. It's called the Red Square Nebula, and there's a star in there that's ejecting gas into space, and it might actually be in the process of dying, might explode someday. This is another example of a picture taken with the adaptive optics. This is a movie. This is Saturn's moon, Titan, and 2 stars are actually passing behind it. Titan has an atmosphere, and you can watch the light of the star be bent through the atmosphere of Titan. Did you notice that bump moving around? Watch when this one comes past. You'll see the bump actually on the opposite side as well. So this was done with the 200-inch and the adaptive optics, and you kind of have to be lucky because you can't arrange for that. Like, okay, I'd like to take this moon of Saturn and pass it in front of some stars. It turned out that they had the right telescope with the right equipment in the right place, which is super. And what do you get from that? Well, you get a cool little animation that's a few seconds long and a PhD. So one of our astronomers was able to actually analyze the way that light is refracted through the air on Saturn's moon Titan, and from that make measurements as to where there are jet stream wind belts on that moon, which later helped a lander to be steered properly to land there and helped him get his PhD in astronomy. So that was a good thing. So there's a lot of neat stuff you can do with adaptive optics. Here is Neptune over the course of one evening, and you can watch it rotate, but it's a way for astronomers to catch and make long-term monitoring of the weather on other places. There's one of its moons goes shooting by, and they didn't color correct for the moon itself, so it looks kind of freaky. Now, I guess I should switch gears and talk about the Loch Ness Monster, right? Oh, wait, no. Do you remember about a year and a half ago, NASA was crashing a probe into the moon on purpose? Okay. The idea was to crash this probe into a dark crater on the moon where they think there's ice and then look for material shot out. Well, all of the telescopes on the right side of the planet to observe this event were doing that, as were we at the 200-inch. This is actually a picture from a newer, bigger telescope that didn't have a mirror made at Corning and wasn't using adaptive optics. And to me, this looks sort of like someone's bad proof of the Loch Ness Monster. This dark thing here is actually the crater that the probe was crashing into. So here's our picture, and then we turn on the adaptive optics and it goes to that. So that's kind of a bit better, wouldn't you agree? Now, the unfortunate thing is they picked a crater with a big mountain on the front of it. And at Palomar, we were the first to confirm there was nothing to be seen. It was kind of unfortunate, but it's an awesome picture of the moon. So we didn't get to see this ejected plume of ice and things coming out into space. We had hoped to see that. But yeah, we were the first to confirm there was nothing to see. So that's the way it goes sometimes. Still, if you get a pretty picture out of it, that's not too bad. So we have on occasion also used a system where we have a laser that shines up into the night sky. Now, the whole adaptive optics thing basically works on having a star as a reference point. And if you don't have a bright enough star nearby as a reference point, a laser beam can do that for you. And so there's a picture both in and outside of the dome showing that. All of this is about to get better. I mentioned our deformable mirror is 241 places it bends. We're going to install one in May that has 3,388. And that should allow us to take the highest resolution pictures from the ground of any telescope anywhere, including the one in space named for Edwin Hubble. It's a bit involved. I'm not going to explain the details. I can if you want, but I can show you that it's coming along, because there it is built. Almost exactly the same stuff in there. In fact, every piece but one is installed right now. And they ran it for the first time Tuesday night this week. Now, the new super bendable mirror isn't quite in yet. It will be in May, as I mentioned. So it would be here. It's not there yet. There's the old bendable mirror there. But what they did was they took the whole thing apart, rebuilt it, retuned it, made it better, and then Tuesday night was their night to go, does it still work? And it did, which is really awesome. Last night they were going to try again, but it snowed. So expect to see some very cool pictures coming out of Palomar from this program later this year. Okay, something to stay tuned of. So far, though, we have used that adaptive optics system to begin a few programs where we start looking for planets that go around other stars. And in the process recently, you know the Big Dipper? The middle star in the handle is actually 2 stars, Alcor and Mizar, and if you look through a telescope, you can see other stars too, but we found that the little one, Alcor, actually has another companion star around it, a tiny reddish star. We've also been able to take pictures of planets that orbit other stars, which is not an easy thing to do. In this picture, which looks like some blobs, the light of a star here has been blocked out, and this, and this are 3 worlds that actually orbit that star. They've got very creative names. The full name is actually, of the star, is HR8799. And this is HR8799b, HR8799c. We kind of ran out of names like Andromeda, right, that sound cool. So everything is catalog numbers now, and that's sort of the way it is in astronomy. But to be able to actually photograph planets that orbit other stars is a big step when you consider when I was the age of some of the guys in the front row here, the total number of planets known to orbit any star other than the sun was 0. And now it's over 500. So astronomers are getting very good at finding other planets. And of course, none of that research that's ongoing at Palomar would even remotely be possible if it wasn't for the work done here at Corning, directed by George Macaulay. And I have to tell you, everybody did a really fine job. We're proud of that. We're happy for that. And thank you for having me here tonight.
That was super. Thank you so much. That was just fantastic. You've done it again. And to cap it all, for just a few minutes, Scott has agreed to answer some of your questions. Who's first?
I have to stand where I can see people. Oh, where does our funding come from? So Palomar Observatory is owned and operated by Caltech, California Institute of Technology, and most of the funding comes directly from Caltech and our other research partners, places like Cornell University, which you hopefully have heard of, and Jet Propulsion Lab and some other partners. Basically, the research groups chip in, and that money spread around does operations costs for running everything. Yes? Oh, it might be faster for someone in the booth to take me there, but if people don't mind the flashback, I'll go back to that picture that Edwin Hubble took of Hubble's Variable Nebula. Do I know what I'm... To everybody? To explain field rotation? Maybe we should talk after. That might be the best answer for that one, is you and I can look at the picture and talk about it rather than do field rotation for everybody, if that's okay. Okay, so I'm going to come back to the field rotation question, and then the other question I got asked was, What is that adaptive mirror made of? It's a thin glass mirror with actuators on the back, and if you push too hard or pull back too hard, you can break it. Do we think it'll break? We hope it won't break. Actually, if the engineers do their job right, since the new mirror we're getting is the one in the world, we really don't want to break that. Just like the 200-inch mirror is the one of that in the world, and we don't want to break that either. So, I'm sorry? I don't know the answer to whether that's chemically tempered or not. I suspect so, but I don't want to say too much of it and make it be wrong. Question way in the back corner. In terms of light years, how far has the Hubble seen into space? Well, we think the universe itself is 13.7 billion years old, and there has been talk still a bit out there as to whether that's confirmed or not, about people being able to see some starlight from objects when the universe itself was only a couple of 100,000 years old. So a little over 13 billion years, if that turns out to be true, is how far anybody's seen out, which is pretty astonishing. Yes, sir? The question was, why are we looking at supernova and what does that tell us about the universe? Especially the what? One of the reasons that we look at supernovae in especially distant galaxies is it really gives you a better feel for how often these things happen. And because they're rare in any one particular galaxy, you can also figure out that they do come in different varieties. So what do the different types tell us about what is going on in those galaxies, or physically what's happening in the star to make it do that? I would say the larger answer is that everything that we have, that we're made of, is pretty much the byproduct of what happens deep in the cores of stars and in supernovae. And stars are basically just hydrogen gas only, and they convert that into some heavier elements, but when they blow apart in a supernova, they scatter that everywhere. And that's what you and I and the Earth and everything around us is made of. And that's one personal reason why I think some people are tied back to that, but others just like big things that go boom, right? And these are the biggest things there are. And the physics of what's happening there doesn't happen here on Earth. And so you have an extreme laboratory in space to test these ideas that people may have about what's going on with nuclear chemistry things and these instantaneous events that produce a supernova. I don't know if that was a long rambling answer or a good answer. Or somewhere in between.
I don't want to start a riot, but we've got time for just one more. And Scott is the lucky person who's going to select the questioner.
And what?
You're going to choose which one you're going to take.
I think the youngest person maybe asking would be that fellow right there. How many planets are orbiting around our sun? If you stick with the modern definition of planet, it's 8 of them. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. But if you want to include some of these, like some people have suggested, maybe everything that's big enough to be round, there you would be more than 50 of them. Some of them don't have good names yet. Maybe you'll find good names for them, or more worlds like it. But in our own solar system, those 8 major planets and many, many, many thousands of asteroids and worlds beyond Neptune that are frozen, icy things too. Well, thank you.
Well, Scott, you've really expanded our minds. You've given us some visual treats. It's been a wonderful evening, and at last I know what Pyrex was for. Thank you.
Thanks.
Good.